Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to you all in the MOOC course on plate and shell. Today I will deliver the second lecture of the module 1. As you remember or recall that in the earlier class, last lecture that I concluded, there I discussed the classification of plate theories, fundamentals of plane elasticity, then deflection, slope and curvature of the plate, displacement strain relations, stress strain relations. So, these are the important background required to proceed on other topics of the plates. Classification of plate theories, you have seen that we have classified the plate into 3 categories: thin plate with small deflection, thin plate with large deflection where nonlinearity is produced due to large deflection and geometric nonlinearity. As a result, membrane stress is significant. Then we have discussed the thick plate theory. In the thick plate theory, I have mentioned that if the plate thickness is less than 1/10th of the larger dimension, then plate is classified as a thin plate. Otherwise, if the thickness exceeds 1/10th of the larger dimension, then it is called a thick plate, and thick plate theory has to be modified based upon the shear deformation criteria. Then we have discussed the fundamentals of plane elasticity, how the stresses are denoted, 2 subscripts are used, what are their significance, what is shear stress and what is the normal stress, and what are the concept of principal planes that I have covered. Then in a plate, I have discussed the deflection and slope, how the slope is measured in 2 directions and what is the interrelation between this slope in any 2 mutually perpendicular direction, and what is the criteria that the direction of maximum slope and minimum slope can be related. Then I have told you about the curvature of the plate. Curvature is obtained by second derivative of this deflection function, and very important relationship have been obtained for curvature in any 2 orthogonal directions. That means, curvature we have seen that it is not dependent on the orientation of the axis. So, whatever way you orient the axis, the sum of the curvatures in 2 orthogonal directions remain constant. Then we have discussed the displacement strain relations, and from that we have arrived the stress strain relations for the plate. Now, let us go to today's topic that I want to cover. In today's lecture, I want to cover the theory of bending in thin plate and related assumptions, expression of strain in terms of vertical deflection, effect of middle surface stretching, because the middle surface stretching is neglected in thin plate theory. However, if stretching is considered, then the effect of this stretching will influence, will alter the strain expressions. So, that I will discuss here. Then expression of moments in terms of vertical displacement. Once the stress strain relationship is obtained, we will go for the calculation of stress resultants in the plate, that is the bending moment and twisting moment in a thin plate, and that relationship will derive in terms of vertical displacement and of course, involving their derivatives. Principal moments on any inclined plane and principal directions I will cover, and then equilibrium equations for the plate will be derived. So, now let us see the theory of thin plate, how it is developed. Theory of thin plate has been developed by Love in 1888 using the assumption proposed by Kirchhoff, and hence it is popularly known as Kirchhoff-Love plate theory. You can say that Love has proposed the plate theory, just extending the Euler-Bernoulli beam theory, and Kirchhoff has covered this plate theory in the form of equations. So, some assumptions are made in developing the plate theory of small thickness and small deflection. The following assumptions are made. Okay. The material is homogeneous and isotropic. So, homogeneous material, you mean that in a space variable it does not alter, the property of the material does not alter with the variation of space variable, it remains invariant of the space index. Then isotropic, in any direction the material properties will be same. The deflection is small, that is the basic assumption in thin plate theory, and this deflection is seen to be within 1/5 of the plate thickness. Otherwise, this theory may not give you the sufficiently accurate results. Then the third assumption, which is very important, the normal to the middle surface of the plate before bending and after bending is remains same. This shows that the strain in z direction is 0 and the length of the normal does not change. So, that is very important assumption, based on which we can say that sigma z, that is the normal stress in the z direction, upward direction is 0, and the shear stress components tau xz, tau zx, tau zy and tau yz are 0. We have earlier mentioned that in a thin plate 3 stresses are of importance. One is sigma x and sigma y, tau xy. Sigma x and sigma y gives you the normal stress, whereas tau xy or tau yx, because of symmetry tau xy equal to tau yx will give you the shear stress in the plate. Okay. So, let us see the expression in terms of vertical deflection. You can see here a plate shows along the thickness, okay, and this is the deflected middle surface, this is the dotted line is the deflected middle surface. Because of small deflection, you are seeing this like a straight line, but actually it bends, but for small deflection and small distance it is taken as a straight line. So, theta x is the slope in the x direction. Similarly, in the y direction, which is perpendicular to the board, we will see that theta y is the slope. Now, theta x is slope in x direction is given by del w by del x, that is the partial derivative of deflection function with respect to x. You can see that deflection function is dependent on two variables x and y. So, we have to write in terms of partial derivative. Similarly, theta y slope in y direction will be del w by del y. This is the general description of the plate, where the middle surface is denoted by the dotted line, and you can see that middle surface is through the mid depth of the plate, and all the stresses or stress resultant, that is mx, bending moment in x direction, bending moment in y direction and twisting moment will be referred in the middle surface. Okay. Now, from that figure we can see that the displacement in the x direction, that is the u denoted by u, is nothing but it is given as this. You can see this z is the height and theta is the angle. So, this u can be computed based on this tangent rule, and because this small deflection, so tan theta will be theta. So, therefore, we get u is equal to minus z theta x is equal to minus z d w, that is the partial derivative of w with respect to x. Okay. Similarly, in y direction the strain we obtain as del v by del y, and that is nothing but z into theta y, and it will be minus z del w by del y. So, two strain expressions we have obtained, epsilon x and epsilon y. Epsilon x is equal to del u by del x and epsilon y is equal to del v by del y, which you can see it is related to the curvature, but it is multiplied with a variable z. That means, knowing the curvature, it can be seen that strain varies linearly along the depth. Okay. If we measure the depth or if we measure the vertical distance referring the middle surface as the datum, we can show the strain variation along the depth of the plate or thickness of the plate. Now, shear strain is given by the expression, that expression we have developed in the first class on the fundamental of elasticity, that is del u by del y plus del v by del x, that gives the two angle on the because of deformation of the plane surface, and because of that the angle that you added is nothing but is a tangent of angle, but because of small deflection we have taken tan theta equal to theta. So, this expression gives you 2 z del square w del x del y. Okay. Here also I have mentioned the undeformed surface and the deformed surface. Undeformed surface is the middle plane straight, and deformed surface you can see here, it is the deformed surface. So, in the next page also I have shown you that this is the undeformed surface and this is the deformed surface, and normal to this deflected surface is shown, which remains same, which remain again normal to the deflected surface. So, length of the normal does not change, that indicates that the strain in the vertical direction is 0. Okay. So, these are the three important relation sigma x, sigma y and gamma x y that we obtain for normal strain in x direction, y direction and shear strain to be used for developing the expression for bending moment and twisting moment. Okay. Now, in thin plate theory generally we neglect the middle plane stretching, but suppose we want to extend this theory including the middle plane stretching, then what will be the change in the expression that we have derived. Okay. Let u naught x y z and v naught x y z are displacement of middle surface by the action of in plane forces. Okay. So, when the membrane force or in plane force acts, then u naught and v naught are the displacement function in x and y direction. Okay. At the middle surface z is 0, because middle surface is our datum. So, naturally at the middle surface we can refer u naught and v naught just as a sole function of this x and y variable. There cannot be any z, there is no significance of z in the u naught and v naught in the middle surface. Okay. Now, let alpha x y be the slope in x direction and beta x y be the slope in y direction. I have taken alpha and beta with a different symbol not to confuse with the slope that we obtained when the middle surface stretching was neglected. Okay. Now, you can see here u x y z will be equal to u naught x y, that is the middle surface displacement due to stretching, then z into alpha. So, z is a, suppose this is your slope in x direction. So, z into alpha x y. So, slope is again a variable involving two index. So, x and y are involved in slope also in x direction. Similarly, the displacement in y direction, that is v x y z, is shown as middle surface stretching plus the stretching or the extension that is developed due to bending of the plate, that is z into beta. Okay. Assumption is thin plate theory is that the gamma x z is 0 or gamma y z equal to 0. So, taking gamma x z equal to 0, we get alpha is equal to alpha plus del w by del x equal to 0. This shows that alpha is equal to minus del w by del x. Okay. Similarly, we get gamma y z. Here gamma y z you can see del v by del z, del w by del y from the plane elasticity equation, and here we get beta plus del w del y equal to 0. This gives you beta equal to minus del w by del y. Okay. Hence, we can write epsilon x and epsilon y considering the middle surface stretching in a modified form. So, epsilon x and epsilon y will be now in a modified form, because these extra terms are coming, del u naught and del v naught terms are coming. So, therefore, gamma x y will be del u by del y and plus del v by del x is also written. So, you can see the change in the strain expressions because of medial surface stretching. However, in the thin plate theory, we simplified the analysis, neglecting the medial surface stretching. Okay. So, in the thin plate theory, we will use this expression for epsilon x, epsilon y, gamma x y. There will be no u naught and v naught terms which indicate the medial surface stretching. Okay. Now, let us obtain the expression for stress resultant. So, very important stress resultant in the plate is the bending moment, because the plate resists the load by bending action or flexural action in both the direction, in x direction, y direction. Also, because of shear stress, the twisting moment is developed. So, let us obtain the three quantities, three expressions mx, my and mxy. Okay. Now, take a side, two adjacent side, one is parallel to x axis and another is parallel to y axis. Okay. When this side is parallel to x axis, okay, and if I take the stress, normal stress, it will be sigma y, and total force will be on the element will be sigma y into dx. This will be the total force on the element. Now, first we are considering the bending moment about x axis. So, we are considering the stress normal to the this phase, that is normal direction is along the positive direction of the x axis. Okay. So, here you can see we have considered a small element in the plate, and here the thickness is dz and the height of the element above the middle surface is z. We have taken a unit width of the plate. So, the force is sigma x into dz into 1 is the area, and force into distance will give you the moment, and if we integrate from minus h by 2 to plus h by 2, we will get the total moment. Now, substituting the sigma x that we have obtained in the previous lecture, the expression for stress in terms of curvature, there we substituted here and then integrating with respect to z. So, z square dz has to be integrated, that means z cube by 3, and then we have to put the limit minus h by 2 to plus h by 2. As a result, you will get this constant E h cube by 12 1 minus nu square. Now, you can realize that if a unit width of the plate is taken and h is the thickness. So, 1 into h cube by 12 is the moment of inertia of the section of unit width. So, this represent h cube by 12 represents the moment of inertia of the section of a unit width, but additional term that 1 minus nu square appears here because of the 2A actions. So, now this is the expression for bending moment. You can easily recognize that this is a constant term which is generally termed as flexural rigidity of the plate. This is the curvature in x direction plus mu is the Poisson ratio into curvature in y direction. Okay. Same logic applied to the bending moment in y direction. So, here in the y direction we have taken a strip here, unit width 1 and the thickness of the element is dz at a distance z. So, similarly we have found the moment here for elemental area, and then we have integrated across the thickness minus h by 2 to plus h by 2, and we get this expression. So, after simplification we get my is this much. Now, let us come to the twisting moment. Twisting moment is resulted due to shear stress. So, shear stress tau x y acting on a element dz will give you the shear force tau x y dz into 1, this is the force, and its moment about this neutral axis or middle surface will be tau x y z dz into 1, and when it is integrated between the limit of thickness minus h by 2 to plus h by 2, we will get the moment expression, twisting moment expression as E h cube 12 1 minus nu square into 1 minus nu del square w del x del y. This expression can be simplified because 1 minus nu square can be written as 1 plus nu into 1 minus nu. So, after simplification and denoting the E h cube by 12 into 1 minus nu square as a flexural rigidity of the plate with a notation D, capital D, we can now express all the stress resultant, important stress resultant, that the bending moment is mx, my and mxy as this. So, mx is minus d bracket del square w del x square plus nu del square w del y square, then my, you can see the expression can be written just changing the curvature, okay, interchanging the curvature. So, here this del square w del y square is coming, and with Poisson ratio you will get the multiplying factor as the curvature in the x direction. So, mxy is written here which denotes the twisting moment. Okay. So, bending moment, shear force and twisting moment in the plane which is oblique to the original x y direction can be also obtained by resolving the vectors. The double arrow is used as a vector to understand this direction of the moment. Okay. So, this is the expression that we obtain for the moment along the normal. So, what is this? These are the moment in the two mutually perpendicular direction, n direction and t direction. So, t direction is your this tangential direction to the plane, and n direction is the normal direction to the plane. So, two expressions are obtained which involve the orientation angle alpha. So, orientation angle if known, we can find the moment in the two orthogonal direction in any oblique plane by this expression. Okay. The plane in which the twisting moment m and t vanishes is called as a principal plane of the moments. So, this can be obtained by equating this expression to 0 and finding the value of tan alpha. So, tan 2 alpha is found like that, and substituting this alpha value in the previous expression, we can get mn and mnt. Okay. So, these are the value of mn and mnt maximum and minimum. Okay. Now, let us find the equilibrium equation of the thin plate. Okay. The governing differential equation of equilibrium has to be known, because otherwise we cannot solve for the deflection. Okay. To find the governing differential equation of equilibrium, let us consider a small element of the plate dx by dy, okay, as shown here, and the direction of the axis is shown in the adjacent figure x y z. Okay. We draw in a magnified scale the element and show all the forces, okay, like a free body diagram. So, the side of the element parallel to x axis is dx and parallel to y axis is dy, and the thickness of the plate is h. Okay. Thickness of the plate is h. This is dotted line is denoting the middle surface. All right. Now, here you can see that on that side the angle is mx, on the opposite side the angle the moment about the x axis, okay, about the y axis. Actually, moment along the x axis is mx, but mx is the moment about the y axis. About and along, two terms are used, you should distinguish between them. Mx, when we call the bending moment along x direction, we denote the bending moment by mx, but this bending moment is actually bending moment about y axis. So, similarly same meaning is applied for my. Okay. So, if on this this side it is mx, on the far side there will be some increment. So, this increment is found by Taylor series expression, and keeping only the first term, neglecting the higher order term. So, this term is mx plus dmx by dx into dx, and twisting moment is shown here, say mxy, and on the opposite faces the increment is also added in the twisting moment. Okay. On the edge which is parallel to x axis, that is perpendicular to y axis, the principal moment is my, here my, and on the opposite face it will be my plus some increment. Okay. So, this increment is found from Taylor series expansion. Taking dx is very small quantity, then we expand it Taylor series and we retain up to the first term and get this quantity. So, mxy is also given here. Actually, I did not distinguish between mxy and myx to write the expression in figure, because you know that from symmetry mxy should be equal to myx. Okay. So, it is written mxy, and on that side the increment is given mxy plus dmxy dy into dy, and the vertical load that is applied on the plate is qxy, which is continuously distributed. That means that qxy is not discontinuous for the deriving the equation of the equilibrium. We take it on the element or throughout the plate it is distributed. When the concentrated load comes, then of course, this equation cannot be used directly, we have to see this. So, it has continuous distribution, that means this function can be differentiable. Okay. So, we have shown all the forces acting on the element, then the shear, vertical shear on this edge is qx, and on the opposite face it will be qx plus increment. Then on the edge which is parallel to y axis, it is qy, vertical shear. Then on the opposite edge it will be qy plus dqy by dy into dy. You can see the directions of forces and moments in the two opposite edges are taken of opposite side. This is because to keep the body in equilibrium. Okay. Then one important thing is that all the quantities that I have mentioned here, mx, my, qx, qy, mxy, all are quantities per unit width of the plate. So, suppose the bending moment unit is say kilonewton meter. So, in the plate problem it will be described by kilonewton meter per meter. Suppose the shear force unit is kilonewton, in the plate problem it will be described by kilonewton per meter. So, all quantities are per unit width of the plate. Okay. Now, in the middle plane it is very convenient to show the moment by double arrow. The meaning of double arrow or the use of double arrow in expressing the moment can be understood by this simple the right hand screw rule. Okay. So, suppose our thumb, this is the direction of moment. So, if I curl the fingers along the direction of rotation, then thumb will point towards the vector. So, moment vector is towards the thumb. So, this actually the moment vector is expressed or written by double arrow. Okay. So, double arrow is used here in the moment vector, and that we have seen in the middle surface the existence of moments and the shear forces. Then taking the equilibrium equation, okay, what are the equilibrium conditions that have to be written? One is bending moment about x axis, mx equal to 0. Then bending moment along x axis, not about x axis, bending moment about x axis, summation of all moments about y axis, that is bending moment along x axis is 0. So, by that equation we get these quantities, okay, and we substituted is all the terms we have substituted from free body diagram and equated to 0. So, neglecting the product of dx square, okay, dx square has to be neglected because it is a small quantity. So, square of small quantity again it will be square. Okay. So, naturally we will neglect this. in the derivation. After neglecting and division by dx dy, we ultimately get an equation of equilibrium in terms of moment del mx del x plus del mxy dy del y equal to qx. Similarly, by summing up all the moments and equating to 0 about the x axis, that means moment along the y axis, we get this equation del my del y plus del my x by del x equal to qy. So, these two equations are very important, which relates the bending moment, twisting moment with the shear force. So, bending moment and twisting moment are related to the shear force. You can understand the significance of this each of the term, the rate of change of bending moment along the x axis will give you shear force in the x direction. Vertical shear along the x axis. But here if you see that del mxy del y, this is the rate of change of twisting moment along y, has to be added to obtain the vertical shear along the x direction. Similarly, here you can see here with the rate of change of bending moment along y axis with respect to y, that is equal to qy, but added term is there because of twisting effect, and the rate of change of twisting moment is added along the x direction. So, you are getting the qy. So, these two equations should be noted very carefully only for this term, which is slightly non-conventional compared to our beam. So, in beam theory only this term was there, but here we are getting additional two terms for twisting effect. So, summing up all the forces in z direction, now we get the vertical equilibrium of forces dqx into del x plus del qy by del y plus qxy equal to 0. Substituting above equations, in the previous slide we have obtained the qx and qy. Now, in the next slide, instead of qx and qy, we will substitute the expression that we have obtained earlier. So, by substituting this and with differentiation, we will ultimately arrive a equation of this type, which is the equilibrium equation of the plate in terms of moment. Now, substitute the expression for mx, my and mxy that we have obtained in terms of displacement and their derivatives. So, if we substitute mx, my and mxy in this expression, then we will obtain very well known plate equation in this form. So, rewriting equation this 36 involving this curvature expression, then we will get this expression, and after doing this some algebra, we ultimately arrive at the equation of plate flexural rigidity d multiplied by del to the power 4 w del x 4 plus 2 del to the power 4 w del x del y square del to the power 4 del y to the power 4 bracket closed equal to q x y. So, if I denote del 4 as the biharmonic operator, then in a compact form I can write the plate equation as d del 4 w equal to q x y, where del 4 is the biharmonic operator. So, this operator is very well known operator in our mechanics problem, and we should use this equation whenever we write in a compact form. We can write d del 4 w equal to q x y. Now, there are other possibilities of expressing the plate equations. What are these possibilities? Let us see. An alternate form of plate equation in Cartesian coordinate system can also be written. So, in that case we obtained a second order equation. So, second order equation can be conveniently written expressed using the Laplacian operator, and which represent the equation of the stress membrane. So, in this slide, let us again write the expression for mx and my and add these two quantities. So, after adding m x and my, we get minus d 1 plus nu del square w del x square plus del square w del y square. So, now letting this m x plus m y divided by 1 plus nu into d equal to m, or d we have not written, d we will keep in the equation. So, we will tell that m x plus m y divided by 1 plus nu as m, a capital M, which consists of the summation of bending moment in x direction and y direction. So, you can see this equation can be written if it is a equation with Laplacian operator. Laplacian operator is del square, okay. Del square is the Laplacian operator, which is del square x square plus del square y square. So, in this way we can write this del square w, and this d term I keep here. So, that this is equal to m. So, del square w equal to minus m by d is one form of the equation representing the deflection with a second order differential equation and relating to the sum of the moment in m x and m y direction. So, you can see that the membrane equation, stress membrane equation is also a second order differential equation. So, here we are getting the equation similar to the membrane equation. So, whatever the equation for the stress membrane is there and solution method is there, can be applied here with suitable change of variables. Now, here original equation in terms of W is del 4 W divided by equal to Q by D, where Q is the distributed load per unit area of the plate, D is the flexural rigidity. Now, this can be broken up as del square into del square W by Q by D. So, del square W again we will take it from this equation. So, if I take del square W here, we can write del square W minus m by d equal to Q by D. So, that gives you another second order equation, but involving the variable m. M is the summation of bending moment in x direction and summation of bending moment in y direction divided by 1 plus nu, where nu is the Poisson ratio. So, conveniently the fourth order equation used for plate problem, finding the deflection and thereafter the bending moment shear force, we use the plate equation of fourth order. But if anybody is interested to interpret the results in analogy with the membrane equation, then also the second order equation be used. So, in the next class I will demonstrate the different conditions or different methods of solution, and especially the whatever equations I have derived here, one is fourth order equation, one is second order equation. Fourth order equation is relating the deflection to the distributed load, and second order equation is relating deflection to the a moment quantity. A moment quantity is the summation of two moments. Now, you can see that any differential equation, when you solve an exact solution is obtained, we need to satisfy the boundary condition, okay. Because if the boundary condition is not satisfied, this will not be an exact solution. Therefore, different boundary condition in the plate has to be known, and based on the different boundary conditions, different methods of solution have been evolved. In theory, generally in exact solution, no definite method is used. As I have told in the introductory class, there is two popular method, one is Navier method and another is Levy's method, but Navier method is used for a plate which has all the edges, all 4 edges is simply supported, that is it is used for rectangular plate only. So, rectangular plate has 4 edges, so all 4 edges are simply supported. Similarly, another method I have told you, that is the Levy's method, which has 2 opposite edges simply supported and other 2 edges may have any other condition. So, these two popular analytical methods are still existing, and results from these two popular analytical method forms a benchmark result. Whatever you use, finite difference, finite element or any other software to evaluate the stress resultant, this method, that Navier method and Levy's method, give you the exact values, and you can compare the efficiency of the software or the numerical techniques. Okay. So, thank you for today's lecture. I will conclude now, and next class we will see how to go into the deep of the plate equation and its solution. Thank you.